Hi everyone, my name is Yohana Jayanti Aruan. Today I would like to present you my paper seminar for ICT Convergence class called NFV and SDN as a key technology enablers for 5G networks. This paper written by Faqir, Zarrar, Yousaf, Michael Bredel, Sibylle Schaller, and Fabian Schneider. Enjoy! But before I start my presentation, I would like to introduce you myself. My name is Yohana Jayanti Aruan, like I said before, but you can call me Chio. I came from Indonesia and I got my bachelor degree in electrical engineering from Telkom University, Bandung, Indonesia. And my work experience is I'm a telecommunication engineer in Telkom Indonesia for 4 years. And my research interest is network architecture technology, 5G ready network. That's why I came up with this paper that related to my research interest. One of the best quote I found came from Nelson Mandela. This quote actually wanna talk to me personally that everything happened for a reason. No matter it's bad or good, you can learn from everything. Every experience you've got, you can learn from that. And just live your life. Before I begin and digging to this paper, I would like to tell you what is the motivation and contribution behind this paper. The first motivation is identifying varying requirements for 5G networks, and then proposing NFV and SDN as key technology enablers for 5G networks. And what's the contribution? Presenting 5G slicing concept and challenges, proposing the marriage of SDN and NFV, providing a detailed introduction to NFV and MANO system. So basically this paper tried to provide a complete overview how to utilize SDN and NFV as perfect challenges faced by 5G networks. Before we jump into the paper, I would like to give you the summary of this whole paper. For summary, this paper explores both of NFV and SDN as a solution for 5G networks. 5G network is heavily related to IoT ecosystem, while in the same time also serve diverse customer base with high volume of data and high quality QoS and QoE in customer perspective. This impacted telco operators to expand and upgrading their network capabilities, hence increasing CAPEX and OPEX. And in this regard, telco operators need to modify the network architecture and technology to be agile, flexible, NFV and SDN come to mind to tackle this issue and furthermore enhance 5G network. Communication networks have evolved through 3 major generational leaps following the technology trends and constantly evolving user demands: 1G, 2G, 3G, and 4G. Services are innovating rapidly with exceeding reliance on the mobile network infrastructure for their connectivity needs. With such a diverse customer base, the mobile network not only has to manage the burgeoning data volume, but at the same time ensure that customer service requests are being adequately fulfilled by the network, meeting the respective quality of service or quality of experience requirements. That's why the deployment of 5G required new strategy in mobile edge and core network. The 3 main features that shall characterize a 5G network will be its ability to support enhanced mobile broadband, massive machine-type communication, and the provisioning of ultra-reliable low-latency communication services. 5G systems are required to be cost-efficient, reliable, flexible deployable, elastic, agile, and above all, programmable. The vision of 5G networks discussed above leads to a very important concept of slicing that has become a central theme in 5G networks. Network slicing allows network operators to open their physical network infrastructure platform to the concurrent deployment of multiple logical self-contained networks, orchestrated in different ways according to their specific service requirements. According to NGMN, the concept of network slicing involves three layers, namely, first one, service instance layers, two, network slice instance layer, and resource layer. The service instance layer represents the end user and/or business services provided by the operator or the third-party service providers, which are supported by the network slice instance layer. The network slice instance layer is in turn supported by the resource layer, which may consist of physical resources such as compute, network, memory, storage, etc. Or it may be more comprehensive as being a network infrastructure, or it may be more complex as network functions. In Figure 2, despite this concept where the resources at the resource layers are dimensioned to create several subnetwork instances, and network slice instances are formed that may use none or multiple subnetwork instances. Some of the principal key of 5G mobile network should be seamless and flexible, agile end-to-end service orchestration for each respective service vertical, and enabling end-to-end connectivity services to each service instance, which is also programmable. NFV and MANO systems. The operation of dedicated network middle boxes transfers into the operation of virtual machines and software, which paves the way to reduce capital expenditures by using common off-the-shelf hardware and to apply existing management practices and tools from the cloud computing space in order to automate network operation tasks and reduce operational expenditures. Management and orchestration. In view of the multi-tier architecture vision for 5G and the related slice concept discussed earlier, a 5G network is mainly composed of three layers, namely the resource layer, the network slice instance layer, and the service instance layer. The most relevant NFV MANO framework today is the reference model specified by ETSI and depicted in Figure 3. This framework has three main functional blocks, namely the Virtualized Infrastructure Manager or VIM, the Virtual Network Function Manager or VNFM, and the Network Function Virtualization Orchestrator or NFVO. The NFVO manages network services. The VNF manager is responsible for the life cycle of single virtual network function that constitute a network service. The virtualized infrastructure manager connects to NFV infrastructure like OpenStack cloud system and manage virtual network function at the level of virtual machines and containers. MANO implementation. Several open source and commercial projects aim at implementing a MANO framework, often based on ETSI specification as described. Most of these projects, however, are still in early stage but already demonstrate the abilities and advantages of a holistic service management and orchestration for network function virtualization. As we can see in the slide, there are open source MANO, ONAP or Open Network Automation Platform, OpenBaton, Sonata, or OpenStack Tracker. Management and orchestration of 5G slices. When NFV MANO is compared to the idea of slicing in 5G network as depicted in Figure 4, the VIM corresponds to the infrastructure manager, the VNFM corresponds to the network slice manager, while the NFVO corresponds to the service instance layer. It can thus be inferred that the ETSI NFV MANO system has the required building blocks for providing a MANO framework for the 5G network slices. Okay, after we finish talk about NFV, now we'll move on to another key enablers for 5G networking, which is software-defined networking or SDN. What is SDN? SDN comes into play to overcome the limitation of traditional networks and traditional network operations. The motivation was to break up ossified networks by replacing rigid hardware-based proprietary equipment and services with deeply programmable common software-driven services and methods that span across multiple vendor platforms. Okay, in this slide I will talk about OpenFlow and ONF. An important protocol in the space of SDN is OpenFlow. OpenFlow enables the communication between network infrastructure elements and network controlling software-based entities. OpenFlow is maintained by the Open Networking Foundation or ONF, and today is supported by all major network equipment vendors. SDN works in the following three principles. The first one is decoupling of control from traffic forwarding and processing. The next one is logically centralized control. Logically centralized means that control appears from the outside application perspective as a single entity, but it is not implied to be deployed in a centralized monolithic implementation. And the last one is programmability of network services. Interfaces between SDN components expose resource abstractions and state. The next slide is SDN implementation. SDN system developments are buzzing with new commercial and non-commercial network hardware, like switches, routers, and software, like SDN controllers. For the hardware, at the advent of SDN dedicated silicon was not available. SDN switches were and still are implemented using either firmware that was translating SDN control protocol abstraction into the switching chips tables or by leveraging already programmable hardware such as network processing units and FPGAs. Similar to SDN hardware, a diversity of SDN controllers has been developed meanwhile too and are available either on commercial basis or as open source. Future direction in SDN research. The initial ideas that lead to the inception of SDN and OpenFlow came from the researchers' desire to be able to innovate more freely and to be able to experiment with new internet architecture. However, limitations still exist when users want to define their own new data plane protocols on which they want to match. Thus, enabling flexible matching on arbitrary header fields has been a recent topic of SDN research and standardization. Keywords in this context are protocol-independent forwarding, protocol-oblivious forwarding, or deeply programmable networks. In order to fulfill the requirements of 5G network, this paper proposed the concept of combining or marriage between SDN and NFV. Like we talked before, we already talked about NFV and SDN. So how about the marriage of both of them? In picture 6, however, we could see different views of chains of command in the cloud or DC or IT views, and the telecommunication world in the right. Telco's main pieces of infrastructure is the network which is controlled by NC. In these NFV times, several of the more complex network elements which were previously managed by the network controller are now deployed as virtual machines. Thus, the network controller will instruct the virtual machine management to instantiate a VNF. To summarize, in both cases, the network controller or the virtual machine manager are just seen to provide the service to the other. In order to bring these two words together, we need to put them on the same level and integrate them further. The virtual machine manager and the network controller will become components of a single infrastructure resource controller. This is already supported by the ONF SDN architecture when assuming that the infrastructure can include compute and storage resources beyond the typically discussed network resources. When integrating the SDN functional components within the NFV infrastructure, it must take into consideration the SDN interfaces relevant for its requirements. Figure 7 gives a high-level overview depicting NFV perspective on interfacing with the SDN domain. As shown, NFV is in the process of specifying the orchestration interfaces for interfacing the SDN control with the NFV mono system. This one is SDN control and this one is NFV mono. This specification takes the interfaces internal to the SDN domain into account. This is the application control interface that provides to the VNFS an application programmatic control of abstracted network resources, and the resource control interface for controlling the NFV infrastructure network's resources. Figure 8 gives different options of integrating the SDN system, like application, resources, and control in the context of NFV, and provides an overview of each option and its combination. The key point is that NFV aims at leveraging the programmability feature of SDN in order to implement network services that may be designed according to some pre-configured VNF forwarding graph, or implement NS that may require the chaining of VNFs based on some policy or service, or even based on VNF processing. For example, a security-related VNF may want to change the path of traffic on the fly depending on its processing output. The SDN controller then establishes the connectivity services by configuring the forwarding tables of the underlying VNF or PNF. Although shown as a separate functional entity, the SDN controller can also be part of VIM or WIM. And at the time of writing this paper, I read that the Infrastructure and Architecture or IVA working group of the HCISG for NFV is specifying use cases for multi-site connectivity in order to draw more concrete requirements for the node-bound interface of the SDN control in order to achieve a happy, successful marriage between NFV and SDN. After all the explanation about this paper, the conclusion I've got is NFV and SDN technology are widely considered as the key enablers in running networks over 5G slices. And standardization will be addressed as research challenges and issues in order to ensure a healthy conception of the envisaged 5G system. Okay, that's all I think for the paper called NFV and SDN as a key technology enablers for 5G networks. I hope you and I will get a new insight about these two technologies. Okay, that's all for today. Thank you everyone for your attention and see you next time. Bye.